December 1941, Pearl Harbor burns. America mobilizes for war it didn't want, but must win. In a Wright Aeronautical Corporation facility in Paterson, New Jersey, engineers stare at blueprints for an engine that shouldn't exist. Royal metallurgists declared no alloy could withstand the temperatures. German engineers calculated the physics made it impossible. Yet America's survival demands the impossible. An engine powerful enough to carry 10 tons of bombs, 8,000 miles. The B-29 Superfortress needs a heart, and if metal won't cooperate, they'll remake metal itself. February 3rd, 1942, 6:47 a.m., Paterson, New Jersey. Temperature 18 degrees. The Wright Aeronautical Facility hummed with the metallic symphony of war production, 3 shifts running without pause. The acrid smell of machine oil mixing with coal smoke from furnaces burning day and night. Outside, fresh snow-covered streets where women replaced men on assembly lines. Inside Building 7, 43 engineers faced a problem that military brass said would lose the war. No engine existed that could power Boeing's revolutionary B-29 bomber. The numbers were brutal, inescapable mathematics written in blood. Current bomber engines, the reliable Pratt & Whitney R-2800, the workhorse Wright R-2600, delivered 2,000 horsepower maximum. Boeing specifications demanded 2,200 horsepower minimum, preferably 2,500, from an engine that weighed less, burned less fuel, and operated at altitudes where thin air choked conventional designs. The Army Air Forces needed range, 3,500 miles combat radius, to reach Tokyo from Pacific Island bases. They needed payload, 20,000 pounds of bombs. They needed altitude, 31,000 feet, to escape Japanese fighters. They needed all 3 simultaneously, which every aeronautical engineering textbook declared thermodynamically impossible. Between December 1941 and January 1942, 12 experimental bomber prototypes failed catastrophically. Engines seized mid-flight from thermal stress. Cylinder heads cracked at 15,000 feet. Superchargers melted. Pilots reported fires in number 3 engine, number 2 engine, oil pressure dropping, temperature spiking, emergency landing at nearest field. Statistics quantified the crisis. 73% failure rate across all heavy bomber engine tests. Average operational lifespan, 340 hours before requiring complete rebuild. Cost per engine failure, $180,000 in 1942 dollars, equivalent to 40 Sherman tanks. But the real cost measured in lives. Bomber crews dying when engines quit over the Pacific, parachutes opening above water, men disappearing into the ocean's indifference. James Jim Hayward Hobbs, 34, from Akron, Ohio, chief metallurgist, stood before the engineering team on February 3rd with test results that confirmed what Royal Aeronautical Society experts had published in November 1941. No aluminum alloy currently in production could withstand sustained temperatures above 450 degrees without structural failure. The Wright R-3350 design called for cylinder head temperatures of 500 degrees, internal combustion chamber peaks of 2,000 degrees, and exhaust valve temperatures of 400 degrees. The math was simple, brutal. Metal failed, engines died, bombers crashed, the war was lost. Arthur Nutt, 41, from Detroit, Michigan, engine systems designer, had spent 18 years at Wright after graduating from University of Michigan Engineering. He'd helped design the R-1820 Cyclone that powered the B-17. He understood reciprocating engines intimately: intake, compression, combustion, exhaust. But the R-3350 demanded 18 cylinders arranged in 2 rows of 9, dual superchargers compressing intake air to artificial sea level density at 30,000 feet, and fuel injection systems delivering gasoline with laboratory precision. Each component operated at the edge of material science. Together, they created thermal conditions that British Royal Engineers calculated would cause catastrophic failure within 45 minutes of sustained operation. Samuel Sam Chen, 29, from San Francisco, California, thermodynamics specialist, son of immigrants who'd arrived through Angel Island in 1910, brought MIT doctoral research on heat transfer coefficients to the team. His calculations confirmed the nightmare. Conventional cooling fins couldn't dissipate heat fast enough. Engine cores would reach critical temperature in 37 minutes. The expansion coefficients of aluminum alloys used in cylinder construction meant pistons would seize before completing combat missions. Even if engines survived takeoff, they'd fail over the Pacific, condemning crews to death by drowning or Japanese capture. The development narrative began with disaster that made the impossible problem undeniable. January 28, 1942, Edwards Air Force Base Test Facility, California. A prototype R-3350 installed in a B-29 mock-up underwent ground testing. 19 minutes into full-power operation, cylinder number 6 cracked, supercharger bearings seized from inadequate lubrication at high temperature, and magnesium engine components ignited. Fire consumed the test stand. 2 technicians suffered third-degree burns. The engine melted into slag. Wright's military liaison, Colonel Donald Putt, declared the program potentially unrecoverable. Boeing threatened to redesign the B-29 for conventional engines, sacrificing range and payload. The Army Air Forces calculated that without the B-29's strategic bombing capability, defeating Japan would require invasion of the home islands at a projected cost of 1 million American casualties. In conference rooms where cigarette smoke hung thick and coffee turned cold in ceramic mugs, stamped with Wright aeronautical logos, the team confronted bureaucratic resistance that matched physics in obstinacy. Procurement officers cited regulations. Metallurgical specifications were standardized. Suppliers couldn't retool for experimental alloys during wartime production demands. Testing protocols required 18 months minimum. Accounting departments calculated costs. Developing new alloys meant $4.7 million expenditure with no guarantee of success, while conventional engines cost $45,000 per unit with proven reliability. Military brass, scarred by procurement scandals from World War I, feared innovation as much as defeat. But Hobbs refused acceptance of failure as inevitable. On February 5, 1942, he presented data from 36 alloy samples tested in furnaces reaching 800 degrees. Sample 17, an experimental aluminum-copper-magnesium-manganese composition with silicon additives, survived 200 hours at temperatures that destroyed conventional alloys in minutes. The formula was unstable, manufacturing tolerances brutal, and no foundry in America possessed equipment to cast it reliably. But it existed. Physics hadn't changed, but human understanding of material science had expanded just enough to glimpse possibility. Arthur Nutt proposed redesigning the entire cylinder head geometry. Instead of conventional cooling fin arrangements, he suggested aviation's first sodium-filled exhaust valves, hollow valve stems containing metallic sodium that melted at 208 degrees, creating liquid metal that transferred heat through capillary action. The concept came from marine diesel engine research. No aircraft engine had ever used it. Testing would require building custom valves that couldn't be purchased, machined by craftsmen who didn't yet exist, installed in engines that weren't finished. Sam Chen calculated that dual-stage superchargers with intercoolers between compression stages could reduce intake air temperature by 180 deg, buying critical thermal margin. But intercoolers added weight, complexity, and 47 additional points of potential failure. Each intercooler required aluminum tubing bent to precise geometries, brazed joints that wouldn't leak under pressure cycling, and coolant systems that functioned at altitude where water boiled at 160 degrees. February 9th, 1942. The decision. Despite regulations screaming no, despite procurement officers threatening resignation, despite metallurgical experts declaring the timeline impossible, Wright Aeronautical committed to building an engine that Royal Engineers said couldn't exist. The team understood the stakes. Every week of delay meant another week Japan controlled the Pacific, another week Americans died on Bataan, another week defeat seemed more likely than victory. The journey was beginning not because success seemed probable, but because refusing to try meant accepting death as inevitable, surrender as acceptable, and failure as America's destiny. They would build the R-3350 because the alternative was unthinkable, and Americans didn't accept the impossible as final. February 1942 through November 1942. 9 months of engineering hell. The Wright aeronautical facility in Paterson operated under conditions that transformed industrial production into warfare by other means. 3 shifts, 24 hours, 7 days weekly. Workers recruited from New Jersey farms, Detroit auto plants, Pennsylvania steel mills, men too old for combat, women whose husbands deployed overseas, teenagers who'd never touched a micrometer. They machined components to tolerances of 0.0001 inches using equipment designed for 0.01-inch accuracy. Fatigue became background radiation, omnipresent and ignored. 16-hour shifts merged into 18-hour shifts as deadlines approached with inevitable cruelty. The foundry where experimental alloys were cast operated at temperatures that turned the facility into a vision of industrial inferno. Furnaces burned at 400-degree Fahrenheit, superheating aluminum-copper mixtures until metal glowed orange-white. Workers in asbestos suits poured molten alloy into sand molds, each casting requiring exact timing because the experimental composition solidified faster than conventional aluminum. Temperature variations of 3 degrees meant scrapped castings. Impurities at concentrations of 0.02% caused crystalline structures that cracked under thermal stress. Of the first 200 cylinder head castings, 178 failed quality inspection. Each failure cost $840 and 3 days of production time. But the 22 that passed represented victory, metal that could survive where British experts said metal would surrender. The valve manufacturing represented nightmare complexity. Sodium-filled exhaust valves required drilling hollow chambers into valve stems, evacuating all air to prevent oxidation, filling chambers with metallic sodium under inert atmosphere, then welding stems closed with electron beam welding that didn't exist in production form. The team recruited welders from Navy shipyards, retrained them for precision work, and built custom welding equipment from salvaged X-ray machine parts. Initial valves leaked, contaminating sodium with atmospheric moisture and causing explosive reactions. The first test engine suffered valve failure at 2,800 RPM, sodium ignited on contact with air, and fire consumed the test cell. 3 workers suffered burns. Testing resumed the next day with redesigned seals because schedule permitted no pause for safety beyond minimum necessity. Environmental challenges multiplied beyond engineering complexity. Winter 1942 brought fuel oil rationing that reduced facility heating, forcing workers to machine components while wearing gloves, which made precision work nearly impossible. Summer 1942 brought heat waves that pushed shop floor temperatures to 110 degrees, where precision instruments calibrated for 70 degrees gave false readings. Workers recalibrated tools daily, checked measurements twice, and accepted that error rates would increase, despite best efforts. The pressure from headquarters never relented. General Henry Hap Arnold, commanding general of Army Air Forces, needed 30 operational B-29s by December 1943. Each B-29 required 4 R-3350 engines. Production schedules demanded 1 engine every 8 hours by September 1943, scaling to 1 engine every 40 minutes by June 1944. Material shortages created cascading crisis. Magnesium for engine cases came from seawater extraction plants on the Texas coast, but German U-boats sank transport ships, interrupting supply chains. Copper for cylinder head alloys required priorities allocation from War Production Board. competing against electrical wire for Liberty ships, brass for ammunition cartridges, and copper for electrical motors. When copper shipments delayed 2 weeks in April 1942, the team substituted aluminum silicon alloys with modified heat treatment, gambling that metallurgical theory translated to practice. 16 test engines ran with substitute alloys. 11 succeeded, 5 failed catastrophically. The 69% success rate was acceptable only because alternatives didn't exist. Human challenges matched material challenges in brutal constancy. Mary Catherine Kate Brennan, 27, from South Boston, Massachusetts, precision machinist, operated the horizontal boring mill that finished cylinder barrels to final dimensions. Her husband, Lieutenant Patrick Brennan, fought with the Marine Corps on Guadalcanal. She received letters weekly until July 1942, then nothing for 6 weeks, then telegram notification. Wounded in action, condition unknown. She continued working 16-hour shifts because stopping meant thinking, and thinking meant imagining possibilities that sanity couldn't tolerate. Her hands, steadied by willpower that transcended exhaustion, machined cylinders that varied less than 0.002 inches across their length. Precision that textbooks declared impossible for manual operations. Robert Bobby Washington, 19, from Harlem, New York, high school graduate who'd planned to attend Howard University before Pearl Harbor, worked as metallurgical test technician. He prepared sample coupons, mounted them in testing fixtures, operated tensile testing machines that measured how much force metal could withstand before fracturing. The work was repetitive, exhausting, and absolutely critical. Every alloy batch required testing before use, and testing meant pulling samples until they broke, recording data, computing statistics, making pass-fail decisions that determined whether $180,000 of engine components proceeded or got scrapped. His supervisor, James Hobbs, taught him metallurgy informally during lunch breaks, explaining crystal structures, phase diagrams, and heat treatment theory. The American pragmatism that accepted talent, regardless of background, contrasted sharply with Axis racial ideologies, and that contrast mattered. Armies that wasted human potential because of prejudice couldn't match industrial societies that mobilized everyone capable of contributing. Organizational challenges emerged from military bureaucracy, colliding with engineering reality. Army Air Force's specifications changed monthly as combat data from Europe revealed new requirements. In March 1942, headquarters demanded engines resist saltwater corrosion after Pacific operations showed coastal bases exposed aircraft to marine environments. In June 1942, specifications required engines start reliably at 40 degrees for Aleutian operations against Japanese-occupied Attu Island. In September 1942, new requirements demanded engines tolerate 100-octane fuel with additives that corroded aluminum. Each specification change required redesigning components, retesting systems, and revising production procedures, while maintaining delivery schedules that presumed no changes occurred. Lieutenant Colonel Edwin Sorensen, 37, Army Air Force's liaison assigned to Wright facility, fought daily battles with procurement bureaucracy. Requisitions for experimental materials required justifications, approvals, and processing through channels designed for peacetime commerce, not wartime urgency. When ceramic spark plug insulators cracked from thermal shock, he bypassed normal procurement and personally drove to Champion Spark Plug Factory in Toledo, Ohio, explained the technical problem to their chief engineer, and returned with 40 prototype plugs using boron nitride ceramics. His methods violated regulations systematically. His results kept the program advancing. The initial operational testing revealed problems theory hadn't predicted. May 1942, first complete R-3350 engine completed assembly, installed in test stand, connected to dynamometer measuring output power. The engine started, ran for 7 minutes at 1,800 RPM, then cylinder number 3 cracked from thermal stress concentrated at valve seat. Teardown analysis showed combustion gas temperatures exceeded calculations by 190 degrees because fuel injection timing created local hotspots. Arthur Nutt redesigned injector nozzle geometry, changing spray pattern from conical to fan-shaped, distributing fuel more evenly. Testing resumed. The engine ran 18 minutes before supercharger bearing failure from inadequate lubrication. Sam Chen redesigned oil passages, increasing flow rate 40%, adding pressure relief valves, preventing bearing damage from overpressure. Testing resumed. The engine ran 41 minutes before exhaust valve failure from sodium leak. James Hobbs improved welding procedures, adding post-weld heat treatment that relieved residual stresses. Testing resumed. July 1942. Engine number 12 ran continuously for 6 hours without failure. Power output 2,300 horsepower at 2,800 RPM. Fuel consumption acceptable. Thermal profile within limits. The team celebrated with coffee and handshakes. No alcohol because facility regulations prohibited it. No excessive jubilation because work remained. But they'd proven the fundamental concept. An engine producing 2,300 horsepower could exist. Metal could withstand temperatures Royal Engineers declared impossible. And American industrial capability, combined with engineering determination, could solve problems that Allied experts had declared unsolvable. August through November 1942 focused on reliability. Combat engines needed 350-hour operational life minimum, preferably 500 hours. Early engines averaged 80 hours before requiring major maintenance. The team systematically improved durability, strengthening connecting rods that fractured from vibration, redesigning piston rings that wore excessively, modifying lubrication systems that failed to protect bearings at high altitude. Each improvement required testing, validation, production implementation, then more testing. Workers adapted to routine of constant improvement. Nothing was final, every component subject to revision, perfection being asymptotic goal approached but never reached. November 1942, engine number 47 completed 350-hour endurance test without major failure. Minor issues, oil leaks, worn gaskets, spark plug fouling, required maintenance but didn't cause operational shutdown. The engine met military specifications. Production authorization was granted. The team had built an engine that British Royal Engineers said couldn't exist, using alloys that conventional metallurgy said would fail, incorporating technologies that hadn't existed 2 years earlier. They'd worked under pressure that broke lesser efforts, adapted when materials couldn't be obtained, improvised when equipment failed, and maintained focus despite personal sacrifices that military service demanded from civilians as surely as from soldiers. The operation was progressing. Success wasn't guaranteed. Combat would reveal problems testing couldn't predict, but the impossible had become improbable, and the improbable was becoming operational reality. December 1942 through August 1944. American B-29 Superfortress bombers began operations from Pacific Island bases, flying missions that Japanese strategic planning had calculated as literally impossible. Imperial Japanese Navy intelligence reports from December 1942 analyzed American bomber capabilities with methodical precision. B-17 maximum range 2,000 miles, payload 4,500 pounds, operational ceiling 25,000 feet. B-24 maximum range 2,100 miles, payload 5,000 pounds, ceiling 28,000 feet. Japanese home islands lay 3,200 miles from nearest American bases in the Aleutians, 2,800 miles from Allied-controlled fields in China. The mathematics were simple, inescapable. American heavy bombers couldn't reach Tokyo. Japan was invulnerable to strategic bombing until American forces captured Marianas Islands, which Japanese defenses would prevent until at least 1946. Therefore, Japan had 3 years to consolidate Pacific conquests, fortify perimeter defenses, and negotiate favorable peace terms from a position of military stalemate. February 1943, reports from Japanese observers in neutral Switzerland brought disturbing information. Boeing Corporation testing very large 4-engine bomber, designation uncertain, performance specifications unavailable but rumored to exceed all existing designs. Japanese naval attaché dismissed reports as propaganda intended to affect Japanese morale. Captured American documents from Guadalcanal mentioned B-29 program, but provided no technical details. Imperial General Headquarters filed the information as low-priority intelligence. Even if Americans developed advanced bomber, production and deployment would require years, by which time Japanese defensive preparations would be complete. April 1943. Japanese radar stations on Kuril Islands detected unusual aircraft flying at unprecedented altitude. Radar operators reported contact at 32,000 feet. Speed 350 miles per hour, heading west toward Kamchatka, then turning back toward Alaska. The altitude exceeded known American bomber capabilities by 7,000 feet. Navy headquarters concluded radar malfunction or atmospheric anomaly. When additional sightings occurred in May, analysts reluctantly accepted the data. Americans possessed aircraft with performance characteristics that exceeded Japanese projections by margins that suggested fundamental technological advancement, not incremental improvement. June 1944 brought operational confirmation that shattered Japanese strategic assumptions. B-29s flying from newly captured bases in the Mariana Islands, Saipan, Tinian, Guam, began bombing Japanese industrial targets with precision and payload that made mockery of previous American efforts. The first raid on Tokyo, June 15, 1944, involved 75 B-29s carrying 20,000 pounds of bombs each, flying at 31,000 feet, covering 3,000 miles round trip. Japanese defenses, optimized for intercepting aircraft at 25,000 feet, couldn't reach the American bombers. Fighter aircraft sent to intercept struggled to climb to operational altitude, and those that reached 30,000 feet found their engines losing power in thin air, controls sluggish, climb rates inadequate to pursue bombers that maintained speed and altitude seemingly without effort. Commander Takeshi Nakamura, 34, Imperial Japanese Navy intelligence analyst assigned to Bureau of Aeronautics, Tokyo, authored report dated June 22, 1944, that outlined the implications with brutal clarity. American bombers possessed range, altitude, and payload that Japanese planning documents had declared impossible with current aviation technology. The only explanation was propulsion systems dramatically more powerful than intelligence estimates. Nakamura calculated that B-29 performance required engines producing at least 2,200 horsepower per engine, compared to Japanese Nakajima Hamar engines' 1,900 horsepower and German BMW 801's 1,730 horsepower. The American technological lead represented not quantitative superiority, but qualitative transformation. The Japanese military leadership faced cognitive dissonance that rigid hierarchical culture couldn't resolve. Accepting that Americans had achieved breakthrough, requiring fundamental advances in metallurgy, thermodynamics, and manufacturing, meant acknowledging that Japanese aviation industry lagged by margins impossible to close during wartime. Rejecting the evidence meant ignoring battlefield reality. Lieutenant General Torishiro Kawabe, Deputy Chief of Army General Staff, proposed explanation that preserved Japanese doctrinal assumptions. Americans must be sacrificing engine reliability for temporary performance advantage. B-29s must require extensive maintenance, suffer high failure rates, and prove unsustainable in extended operations. Combat data would reveal American engines failing, bombers aborting missions, and strategic bombing campaign collapsing from mechanical unreliability. July and August 1944, combat data contradicted Japanese predictions systematically. B-29 operational sortie rates increased from 75 aircraft to 150 aircraft per raid. Maintenance data from captured American technical documents showed R-3350 engines averaging 400-hour operational life between major overhauls, substantially better than Japanese Army Ki-61 fighters' Che-40 engine, which averaged 180 hours. Abort rates from mechanical failure decreased from 18% in June to 9% in August, indicating reliability improvements during combat operations, not degradation that Japanese doctrine predicted. Captain Saburo Sakai, 28, Imperial Japanese Navy fighter ace, 64 confirmed victories, authored after-action report, following encounter with B-29 formation near Tokyo, August 7, 1944. Enemy bombers maintained formation at 9,500 meters despite concentrated fighter attacks. Our engines lost power above 9,000 meters. Closing speed was insufficient for effective gunnery. Enemy defensive fire was intense and accurate. I observed no mechanical failures, no straggling aircraft, no evidence of operational difficulties that would suggest unreliable propulsion. The enemy has achieved performance superiority that tactical modifications cannot overcome. Our intelligence estimates were fundamentally incorrect. Indeed, the doctrinal inflexibility that characterized Japanese military culture prevented adaptive response. Fighter tactics remained optimized for intercepting B-17s and B-24s at 25,000 feet. Aircraft production continued focusing on designs that couldn't reach B-29 operational altitudes. Engine development programs, pursuing 2,000 horsepower designs, faced material shortages, lack of specialized alloys, and manufacturing limitations that American industry had overcome through systematic innovation beginning in 1942. By the time Japanese engineers recognized specific technical solutions, sodium-cooled valves, dual-stage supercharging, advanced aluminum alloys, American production had scaled to one R-3350 engine every 40 minutes, creating quantitative advantage that magnified qualitative superiority. The first direct engagement where Japanese command personally witnessed R-3350 reliability occurred August 20, 1944. Formation of 112 B-29s bombed Yawata Steelworks, Japan's largest steel production facility, flying from Chengdu, China. Japanese fighters intercepted, engaging bombers for 40 minutes across 200 miles. Of 112 B-29s, 3 were shot down by concentrated fighter attacks, 2 were damaged and crash-landed in China, and 107 returned to base. Post-strike reconnaissance by Japanese intelligence confirmed bomb damage. Steel production reduced 32%. Captured American aircrew from downed bombers reported under interrogation that their aircraft had flown 11 previous combat missions without engine replacement. The operational reliability defied Japanese engineering assumptions. Metal alloys that withstood sustained high-temperature operation, lubrication systems that functioned at altitude, superchargers that compressed thin air without mechanical failure, each represented technical achievement that Japanese industry couldn't duplicate. September 1944. Imperial General Headquarters acknowledged in classified briefing to Emperor Hirohito that American strategic bombing capacity exceeded Japanese defensive capability by margins that industrial mobilization couldn't close. The Americans hadn't just built better bombers. They'd revolutionized aviation propulsion through metallurgical advances, manufacturing precision, and engineering integration that Japanese industry, operating under resource constraints and damaged infrastructure, couldn't match within militarily relevant time frame. The engine that British Royal Engineers said couldn't exist was burning Japanese cities, destroying industrial capacity and demonstrating technological superiority that shattered strategic calculations. Japanese commanders understood they faced adversary whose industrial innovation exceeded battlefield estimates, whose pragmatic engineering culture solved problems through systematic experimentation, and whose determination to win manifested in machines that performed beyond theoretical limitations. August 15th, 1945. Emperor Hirohito's surrender broadcast ended the Pacific War. Across the Pacific Theater, B-29 crews received stand-down orders, ending missions that had delivered 147,000 tons of bombs on Japanese industrial and military targets. The statistics quantified victory: 33,000 sorties flown, 3,960 B-29s built, 15,840 Wright R-3350 engines produced. Each engine averaged 425 hours operational life, exceeding original specifications by 21%. Engine-related mission abort rates declined from 18% in early 1944 to 2% by August 1945, demonstrating reliability improvements during wartime operations. The immediate strategic impact was measurable. Japanese industrial production fell 83% between June 1944 and August 1945. Steel output dropped 91%, aircraft production decreased 88%. But the lasting historical transformation reached beyond tactical victory. Military historians analyzing the Pacific Campaign identified the B-29 R-3350 combination as pivotal example of industrial innovation changing warfare's fundamental character. Strategic bombing became viable not merely from aircraft design, but from propulsion technology that enabled unprecedented range, payload, altitude combinations. American ability to develop advanced engines in less than 3 years, from initial design February 1942 to combat deployment June 1944, represented manufacturing capability that Axis powers couldn't match. German Jumo 222 program, attempting similar performance goals, never achieved production despite beginning in 1938. Japanese Nakajima Ha-54 program, targeting 2,400 horsepower, remained experimental through war's end. Only American industrial culture, combining academic research, corporate engineering, and military requirements into unified development effort, succeeded in translating theoretical possibility into operational reality. The metallurgical advances pioneered for R-3350 production created post-war industrial revolution. Aluminum-copper alloys developed for cylinder heads became foundation for jet engine components in 1950s. Sodium-cooled valves transitioned to automotive racing applications. Precision casting techniques, enabling complex geometries with tight tolerances, became standard aerospace manufacturing practice. The wartime crisis forced innovations that peacetime research might have pursued leisurely across decades. Necessity compressed development cycles, bypassed bureaucratic barriers, and funded experimentation that commercial markets wouldn't support. The cost was immense: $2 billion in 1945 dollars for total B-29 R-3350 program. But victory justified expenditure that defeat would have rendered irrelevant. The individuals who transformed impossibility into operational equipment returned to peacetime lives bearing permanent marks from their crucible experience. James Hobbs continued working at Wright Aeronautical until retirement in 1967, eventually becoming Vice President of Metallurgical Engineering. He authored 12 technical papers on high-temperature alloys, consulted for NASA Apollo program on spacecraft materials, and mentored generation of engineers who built America's aerospace industry. In 1983, interview for Smithsonian Oral History Project, age 75, he reflected, "We didn't think about whether it was possible. We thought about what would happen if we didn't try. The metal didn't want to cooperate, but metal doesn't have opinions. Physics is negotiable if you understand the right questions." Arthur Nutt returned to Detroit, joined General Motors, and led engine development programs, producing first mass-market fuel-injected automobile engines in 1957. His sodium-cooled valve technology, pioneered under wartime pressure, became standard in high-performance engines. He held 47 patents at his death in 1979. His obituary in Automotive Engineering magazine noted, "Nutt's wartime innovations proved that American engineering culture, pragmatic, experimental, willing to fail and learn, was itself strategic weapon as powerful as any bomb or bullet." Sam Chen completed PhD at MIT in 1947, joined NACA, predecessor to NASA, contributed to supersonic aircraft development, and eventually became professor of aerospace engineering at Stanford University. His thermodynamics research enabled jet engines, rocket propulsion, and spacecraft thermal protection systems. Students remembered him teaching that theoretical limitations were starting points for negotiation, not final answers. He emphasized that Chinese-American engineers faced discrimination despite wartime contributions, and he spent career advocating for meritocracy in engineering hiring. His legacy included not just technical achievement, but cultural shift toward judging engineers by competence rather than ancestry. Mary Catherine Brennan's husband, Patrick, returned from Pacific service in November 1945, wounded but alive. She continued as precision machinist, eventually becoming shop supervisor, first woman in that role at Wright facility. She trained returning veterans in precision manufacturing techniques, emphasizing that wartime necessity had proven women's technical capability. Her career demonstrated that gender barriers in technical fields were cultural constructs, not natural limitations. She retired in 1974, having machined components for jet engines, spacecraft, and commercial aircraft. Her obituary in 2003 noted, "She machined parts for the engine that won the Pacific War, then spent 30 years proving that wartime emergency should have been permanent revolution in workplace equality." Robert Washington attended Howard University on GI Bill after Navy service in Pacific Theater, earned engineering degree, joined Boeing in 1950, and contributed to 707 jetliner development. He became one of first African-American senior engineers in American aerospace industry. His career demonstrated that wartime integration of industrial workforce, driven by necessity, created precedents that civil rights movement expanded into legal equality. He later reflected that learning metallurgy from James Hobbs during lunch breaks at Wright facility taught him that knowledge transcended racial barriers that society constructed. The official military recognition came slowly, delayed by secrecy classifications. The Manhattan Project dominated public consciousness as weapon that ended the war, overshadowing conventional bombing campaign that destroyed Japan's industrial capacity before atomic weapons deployed. But strategic analysts understood B-29 campaign forced Japanese resource diversion to homeland defense, demonstrated American industrial superiority, and made invasion planning credible by degrading Japanese military production. The R-3350 engine enabled every mission, and engine reliability determined strategic bombing campaign sustainability. In 1995, Smithsonian Air and Space Museum curated exhibition titled "The Engine That Wasn't Impossible," featuring restored R-3350, alongside metallurgical samples, original engineering drawings, and oral histories from surviving engineers. The exhibition text explained, "British Royal Engineers declared no alloy could withstand the thermal stress. Japanese strategists calculated that American bombers couldn't reach their homeland. German intelligence estimated American industrial capacity couldn't scale production to operationally significant levels. All were wrong not because physics changed, but because American engineers refused to accept theoretical limitations as final answers. They developed new alloys, redesigned cooling systems, improved manufacturing precision, and scaled production to industrial levels unprecedented in aviation history. The result was a weapon that changed strategic balance through engineering determination, not exotic physics." The final validation came from enemy acknowledgement. Post-war interviews with Japanese military officials revealed consistent theme. Underestimating American industrial innovation capacity was strategic mistake equivalent to tactical defeat. Vice Admiral Takejiro Onishi, architect of kamikaze tactics, stated in 1946 war crimes trial testimony, "We calculated American production capacity accurately. We failed to calculate American innovation capacity. They built engines we thought impossible, flew them reliably for years, and demonstrated industrial culture that treated obstacles as problems requiring creative solutions rather than absolute limitations. Our rigid adherence to established doctrine prevented adaptive response. Their pragmatic experimentation enabled continuous improvement. That cultural difference determined the war's outcome as much as any battle." The R-3350 story entered American cultural consciousness as exemplar of national character. Determination to overcome obstacles through innovation rather than acceptance of limitations. Collaborative effort combining government, industry, and academia. Willingness to risk failure in pursuit of necessary success, and pragmatic engineering culture valuing results over theoretical purity. The individuals were ordinary Americans from ordinary places, Akron, Detroit, San Francisco, Boston, Harlem, who accomplished extraordinary things because circumstances demanded it and culture enabled it. 70 years later, Wright R-3350 engines remain displayed in aviation museums worldwide. Polished aluminum cylinders and complex supercharger assemblies representing moment when America proved that impossibility was negotiable. The plaques note technical specifications: 200 horsepower, 18 cylinders, dual superchargers, 350-hour operational life. But the deeper legacy transcends engineering specifications. The R-3350 demonstrated that when free society mobilizes industrial capacity, combines diverse talent without arbitrary restrictions, embraces experimentation over dogma, and refuses to accept defeat as inevitable, theoretical impossibility transforms into operational reality. Metal that Royal Engineers declared inadequate became metal that powered bombers across Pacific distances previously considered insurmountable. And the engineers who created it proved that American innovation, determination, and pragmatic problem-solving constituted strategic advantage as decisive as any weapon, an advantage that won the Pacific War and shaped the technological century that followed. That's the story of the Wright R-3350, the engine British experts said couldn't exist, but American engineers built anyway. If you're fascinated by the unsung innovations that won World War II, hit that subscribe button and the notification bell so you don't miss our next deep dive into history's most dramatic engineering triumphs. Drop a comment below. What other impossible wow technologies should we explore? Your suggestions drive our content. Thanks for watching, and remember, the impossible is just engineering we haven't figured out yet.